Okay, hi everyone. So this is going to be a review for test one, and I think this video will be pretty short. I think that we've covered everything we needed to cover, but I still wanted to give you a quick review. Usually with these, what I'll do is kind of do an outline of topics, maybe remind you if there are any formulas you should know, and I'll throw in a couple of examples here and there, but you know, we'll get through it pretty quickly, I think. So first of all, what does the test cover? So I'll put that up here. This covers chapter 4. Well, I use section numbers from a textbook, but I'll go through the outline and remind you what all of this means. But we called it 5.1 through 5.4. Then we did 5.7, and then we did 5.6. That was the order we did them in. So now I'll tell you what are those things. What I'm calling chapter 4 was basically a review of integration that we did on the first day. It might have been the first day and a half of class, and that includes indefinite integrals, definite integrals, a little bit of area under a curve, and then we had the substitution rule. And I'll write a sentence or two, but you know how to do this is you introduce the variable u, and then you find du and substitute into the problem. So I could ask you some integrals that are just normal integrals like this, or they could come up in later sections also, right? Just thinking of a quick example here, 5.7 was improper integrals, and sometimes you might need to do the substitution rule for an improper integral, right? So I could ask you something from this and think of it as a chapter 4 question, or I could just have it appear within those other questions. But let's do a quick one here. I do think that this stuff is really important. You want to be an expert at all of these kinds of integrals right now. So here's one, and I don't know if we've seen this one or not, but I have a couple of examples I wrote for today. So on any of these examples that I do in this video, feel free to pause the video and try it on your own if you'd like, and then check back with me. But I'll go ahead and do these. So this one is a great example of substitution because you see that if you let u equal the function in the exponent, I see it's going to work out beautifully because when I find du, it'll be 6x dx. Now, the original problem doesn't have a 6x dx in it. It does have x dx, so a 1/6 will come out. 1/6 of du is x dx. You've seen how I sort of write these by now. I sometimes will rewrite it to put the x dx together. I like doing that to sort of show myself like that part is becoming 1/6 du, and the rest of it is becoming e to the u. I don't know, I think that's a good way to make sure you don't lose track of anything. Make sure you don't forget the 1/6. But 1/6 is a constant, so it could be pulled out of the integral. Once you get here, you're probably going to be fine. You say, oh, well, the integral of e to the u is e to the u. But don't forget, you have to get this back in terms of x. If it's a substitution rule problem, you'll always have something on your page already for what u is in terms of x. And don't forget the plus c. And make sure the plus c doesn't look like it's in the exponent, right? The plus c is just off to the right. that was kind of the one substitution problem I wrote for today. I just, not necessarily going to show you problems for every single topic today, but I'll just do a few of the highlights. All right, next section was 5.1, integration by parts. So I guess the quick summary is, or maybe the most important thing, is this formula. So you need to know that. We also talked a little bit about sort of a preferred order for choosing which part should be u. We had kind of a list of functions of like logarithmic, inverse trig, algebraic, trig, exponential. So you probably have that in your notes. I'll do an example of this. Now, integration by parts is a formula, but I also think of it just as a strategy. There's a certain way we usually write it. And yeah, by the way, if you compare this to the previous example, you say you have to identify which method to use for which problem. So I want to be clear that on a test, problems are not necessarily in order that we covered them in. Like it doesn't, I don't know what order they're going to be in. You might just be in the middle of a test and see a problem, and it's up to you to figure out, is this an integration by parts problem, substitution rule, something else? I think that I do a quick mental check of would substitution work, and I quickly see that it would not. I mean, what made substitution work so beautifully in this first problem was that this had an x squared and this had an x, so that the derivative worked out well. This time, if I tried to do a substitution, du would not really take care of that x for us. That's why we use integration by parts. For that, we usually set up the 4 pieces that we need. And I think a good choice of u is x, which means dv has to be everything else. So the dv should have a dx attached to it. All right, once you write those, du in this case would be dx, or you could say 1 dx. Over here, I sometimes do scratch work on this kind of step, right? Because this is kind of like a little problem within the problem. And this is a place where sometimes mistakes happen. So you have to be careful, because if you get the wrong v, it's going to throw everything off. We're doing kind of a little integral problem here. And for this, I think we could do a substitution rule. Like that. And a negative 1/3 will appear. So, let's see. Do I have enough room here? Yeah, I think I do. Negative 1/3 integral e to the u du. That's making me think negative 1/3 e to the negative 3x. If this was a problem of its own, I would need a plus c for that, but this was just kind of a side problem in the margin. Over here, we don't need a plus c. That is going to be my v. So I think a common mistake that students sometimes make is they won't have the negative 1/3 here, or maybe they'll have like a negative 3, and it should be a negative 1/3. So be extra careful about that sort of thing. Now I'll use the formula. And I think I've said this before, but when we have a formula like this that's really important, I think it helps if you just write it each time you use it. Helps you memorize things. This looks like this. I have minus something that's negative, so I could make it a plus. And what we're seeing here is this doesn't always happen, but it sometimes happens that you need to integrate something that you've already integrated as part of finding v. So because we already did that work, it'll save us a little step here. So I'm thinking plus 1/3 times this kind of thing is happening again, right? So there will be a negative here, plus 1/3 times something that's negative, and there's a 1/3 times a 1/3, so let's make it 1/9 e to the negative 3x, and now I need a plus c. There's also other ways you could write this final answer. You could, let's see, you could factor out a 1/3, you could factor out a 1/9, you could factor out e to the negative 3x. There's a lot of options, but I think the way we wrote it here is also fine. All right, so moving on to the next section, 5.2 is where we started doing integrals involving trig. So 5.2 was just called trig integrals. All right, so trig integrals includes things such as sine cubed x, or some of those ones that have a sine and a cosine. Some things to know. So we've got this trig identity, which can be rewritten as a couple of different forms, but you could use this for a cosine squared or a sine squared. So that helped us in problems such as ones that had an odd power of sine or cosine, maybe like this one I'm pointing at, the sine cubed. You might use one of these. And then also, we had those double angle identities. And they look very similar, so if you remember one of them, you'll probably remember both. But you kind of have to remember which is which one of them gets the plus sign, and it is cosine. We use those for some problems that had an even power of sine or cosine, like the integral of sine to the fourth. So I'll show you an example. And you could try it if you'd like. So I think the very first time we did a trig function squared was probably sine squared, and we did that in 5.1, which was integration by parts. But that one was kind of messy back when we did that with integration by parts. In section 5.2, we learned, you can use these identities to help out. So what I would do here is use that identity. You have to be a little careful here, though. So the identity expects this to just be an x on the left side. We have a 3x. So if you put a 3x on the left side, you have to put a 3x on the right side. And that's okay. But there's already a 2 there. So 2 times 3x is 6x. You might also be able to kind of do that as a substitution type of problem, but what I just did is also fine. It's like I took this identity, replaced x with 3x everywhere that x appears. I think the way I would do this is, let's see, distribute the 1/2, and we could kind of deal with the easy parts separately. I like that. Distribute the 1/2 and then just say, this part, this is just 1/2 x. And then I could focus in on the tougher part of the problem. But it's not that bad. We just do substitution. So I told you substitution rule can show up in other sections. It doesn't have to just be substitution problem by itself. So 1/6 du equals dx. Let's see, where are we at? Let's just start a new line. So the 1/2 x over there plus this 1/6 times the 1/2 that was already there gets me 1/12 integral cosine u du. So 1/2 x plus, I'll go ahead and integrate this and get it back in terms of x at the same time, but you could do that in 2 steps if you want. Looks like sine of 6x, and I need a plus c. For 5.3, also trig, I might not do an example of that right now. But I know that there is one in that packet I gave you. So trig substitution, I guess, what's the important thing to remember for this section? It's that there were 3 different cases. All right, and last case was secant. That's if it's x squared minus a squared. So I know when we covered that section, we saw all 3 cases come up at least once each. And yeah, that's how you would start it. .4 was partial fractions. Partial fraction decomposition. It's kind of a cool name. It's because we're sort of decomposing a function into like a sum of smaller pieces. So real quick, I just want to remind you of the types of setup that you might have to do. Let's just kind of set up some problems. So let's say you wind up with something that looks like this. This is sort of the most basic case, and I've already factored the denominator. Keep in mind that a problem might give you a denominator that's already factored, or it might be up to you. You might have to factor it. Be careful with your factoring. You could always double check. If you factor something, you're not sure if you did it right, you could distribute, expand, make sure it equals what it should. But the setup for this kind is you would do a over the first factor plus a b over the second factor. That's what I would call kind of the basic case. We did a couple of those. And then we also had a case where you have something like this. And the idea is that x squared plus 1 is irreducible. It's quadratic, right? X squared. But this can't be split up into 2 factors using real numbers. It can't be done. So you do need a over the first factor, but for the x squared plus 1 part, the algebra is not going to work out if you just put a b up there. This is where you have to do a bx plus c. So this is the case I would call irreducible, quadratic factor. And then there was one other case, and that is if you have a factor that appears more than once, such as squared. So that factor is kind of there twice. You can imagine it as like an x plus 2 and another x plus 2. And the setup was a little different for that one. You needed to do a over the x plus 2, and then you needed a b over x plus 2 squared. And I know we did at least one of those. We probably didn't do as many of those. But yeah, I'll just say this is the case that is a repeated factor. Let's see, what else? I also want to say, so that was the setup. I also want to say, remember something that could come up. Is that this equals inverse tangent. Inverse tangent is also known as arctan. I've got one of these problems that we could do right now. So I'll set it up, and remember, you could pause the video and try it. I think this is a new one for us. All right, so remember, these problems are mostly algebra. Like, you could do a lot of this without even having the integral symbol up. Just make sure you integrate at the end. So let's factor the denominator as much as we can. You could factor out an x squared, actually. X squared and then x minus 1. So something to keep in mind is that this x squared is one of these cases, right? And you say, oh, it's quadratic, right? Is it this one or is it this one? Because this is also squared. This counts as a repeated factor because x squared is x times x. So it is sort of a factor of x times another factor of x. In fact, you could put parentheses around the x if you want, and then it looks a lot like the repeated factor case. So what I'm saying is the setup needs to be the setup from the repeated factor case above. Looks like that. With all of these, it seems like what we do is multiply both sides by the denominator from the left-hand side. And when you do that, the left-hand side becomes nice and simple, and the right-hand side also becomes simple because you kind of get rid of some of these fractions. You get rid of the denominators. All right, so I think what we get here looks like this. So I'll say this again. What I just did was took this equation and I multiplied both sides by the denominator from the left-hand side. And then I canceled anything I needed to cancel. You could show more there if you want. You could show canceling and crossing things out. I think we did that the first time we did it. All right, so then usually once you get here, you start distributing because next we're going to sort of combine or group the terms together. On the left-hand side, I have something with an x and then plus 1. On the right-hand side, I have some x squareds, some x's, and at least this constant here. So let's get all of the x squareds together. Let's get all the x's together. So there's my x squareds because there was an ax squared and a cx squared. For x's, I have a minus a and a plus b. And then I guess this minus b. I could write it like that. That's fine. So the system that we have to solve here, I guess we have that a plus c must equal, so the number of x squareds on the right has to equal the number of x squareds on the left. And you say, wait a second, there are no x squareds on the left. Well, you could imagine a 0x squared, right? There's 0 of them. So a plus c must equal 0. And then minus a plus b must equal 1, and this constant must equal this constant. So minus b must equal positive 1. It seems like pretty often when there are 3 letters involved, a lot of times the system will kind of give you one of the answers. So, sometimes I circle these as I go. Oh, hold on a second, though. I don't want to circle that just yet. I want to convert this. There. There's B. Then maybe I'll use this one and say minus a, there's b, so a is -2. And then a plus c equals 0 implies that c, if a is -2, then c must equal 2. So we found all three. Now we can put this all together and integrate. I think I have to move my page, though. All right, let's remember this was an integral problem, so what we just found is that this can be rewritten as -2x, or I should say -2 over x, minus 1 over x squared, and a 2 over x minus 1. And I've already split this up into the three pieces. You could write it as one big integral and then split it up like this if you want. So let's see. This is -2. I'll do this to it. This middle one has an x squared here on the bottom. Think about how you would do that. I think the way I would deal with it is make it x to the -2. Yeah, I like what we've done here. So this is -2 ln, absolute value x. When I integrate this, let's see, there's a minus out front. It's just x to a power, so you just use the power rule, right? Looks like that. And then over here, plus 2 ln, absolute value, x minus 1. We need a plus c, but I'll write it on the next line, because I think I'll just fix this up a little bit. -2 ln, absolute value x. Let's make this a plus 1 over x, plus 2 ln, absolute value, x minus 1. And there's my plus c. So most of the time spent was just in sort of the algebra part of the problem. So be extra careful with the algebra. If you have time, double check your work, double check your algebra. So remember, with that A, B, and C, if you find one of them wrong, it can throw off all the others. Like here, with this B, if I accidentally was too quick and just circled this and said B is 1, like if I used B equals 1, I would get the wrong A, the wrong C, the wrong answer. So B had to be -1. All right, next up, we jumped to 5.7, which is improper integrals. I think I have one of these for us to do. There were two types. So quick summary, this is when infinity and or negative infinity are there as a limit of integration. By the way, that phrase, I guess we don't use it that often, but the limits of integration are basically the a and b that you usually have below and above the integral symbol. They can be called the upper limit and lower limit of the integral. It's like x goes from something to something. Anyway, if there's an infinity symbol or a negative infinity symbol, we turn it into a limit, right? So this is how you would handle this case. The other case is if there's a negative infinity, it would probably be on the bottom, and you also do that as a limit. This time it's a limit as t goes to negative infinity. And when you do these, set it up, and I would like to see you write lim, right? You should write limit t goes to infinity or limit t goes to negative infinity, so I could see what you're doing, and you're putting equal signs between things that are equal, and try to write your work neatly. For most of the problem, you're just dealing with the integral, and then usually the limit is saved for the end. There was also type 2. Let's see, a quick summary of type 2 would be when you have an integral where f has a discontinuity at c, where c is between a and b. So you're trying to integrate from a to b, but somewhere in the middle there's a problem. And that problem is often in the form of something that would be dividing by 0 and something that would be causing a vertical asymptote. So what we do is we split it up and we sort of integrate everything to the left of the problem and everything to the right of the problem, and we might need to do a limit for each of those. So I'll do one of these examples, I think. Oh no, actually, I'm sorry. The example that I have is a type 1. Yeah, we'll do a type 1. I think I wanted to do a type 1 because when we finished that section 5.7, the last couple of ones that we did were type 2, and maybe it's been a little while since we saw type 1. All right, so you could try this if you'd like. I would say a good first idea is to rewrite it as a limit. Sometimes I add parentheses here. You could do that if you'd like. Here, I'll do it in a different color. You could do parentheses like that to sort of emphasize, order of operations is we're going to deal with this integral first and deal with the limit last. I think I'll do some scratch work here. So I think what I'll focus on is just finding this integral first. And, in my scratch work, I wrote it without the 2 and without the t, so we'll remember to put those back in at the end. But this is a little substitution rule problem. I would let u equal the thing that's in parentheses. So this could be thought of as 1 over u squared du, which is the same as u to the negative 2 du. So this is the power rule. We did this a minute ago on that other problem. So what have we got here? I guess this is negative 1 over x minus 1 when I get this back into terms of x. Or I could even make it 1 over 1 minus x. So I kind of put the minus sign on the bottom here. See, the 1 became a positive 1 because it was a negative of a negative. I don't know. I like this last form that I wrote it in. I think I'll use this last form. So that was a problem within the problem, and now let's put this together. Now, that was scratch work, and I guess I'm labeling now evaluate limit. So the limit as t goes to infinity of, let's not forget the 2 and the t. I guess 1 over 1 minus x with the 2, with the t, and then optional parentheses around that if you want to. So at this point, I still can't tell what it is, right? We need to kind of carefully put in the t and the 2, but I think we're getting close to the end of this. Okay, so when I put t in, it looks like this, and then minus, what happens when we put 2 in? Let's figure this out. 1 over 1 minus 2. Let's do this on another line. 1 over 1 minus 2, the 1 minus 2 is negative 1. There's a minus out front already, so this is just a plus 1. All right. Let's think about what happens here. Usually we get to this part and we can kind of figure out what this is approaching. As t goes to infinity, you can imagine a larger and larger and larger number going in for t. T is a million, t is a billion, t is a trillion. But there's a minus in front of it, right? Also, that 1 up top. So the 1 up top is going to become minuscule, insignificant compared to how gigantic the denominator is becoming. So overall, this is approaching 0. So I have a 0 and a plus 1. This becomes 1. So we could say so it converges. If a problem said, does this integral converge or diverge? This one converges. It converges to an answer of 1. So let's talk a little bit about 5.6. So 5.6, numerical integration, we were estimating areas under a curve using rectangles or sometimes other shapes. And I'll tell you the ones that I'm mostly interested in. All right, so since I'm just giving kind of an outline or a summary, I think what I'll do is show you, I'm thinking of the 3 rules that I'm most interested in. I think I'm going to show you the n equals 4 version. So first up, the trapezoidal rule. You know, instead of showing you the real general version with n and then we need to go up to xn, I'm just going to show you this for n equals 4. That's when you're splitting this up into 4 equal vertical strips. You would use this. So in class, we did this mostly for that example of x squared, but I think we did 1 or 2 other examples towards the end. And then next up was the midpoint rule. So I'm sticking with the n equals 4 version right now. So this has delta x times f x1 bar plus f x2 bar, and so on. For this one, I need to say what x bar equals. I'll say xi bar equals halfway between the one that comes before it and the one that comes after it. So I think that in class when we did one with x squared, we were, if I remember correctly, we were splitting up, we were integrating from 0 to 1, and we were splitting it up into n equals 4 equal parts. So when we did sort of the left endpoint method or the right endpoint method, delta x was 1/4. We had these equal strips of 1/4. But when we did the midpoint rule, we had to think about 1/8, right? Because 1/8 was halfway between 0 and 1/4. And I think we did 1/8, 3/8, 5/8. So it's in between the 1/4 in that problem. The other rule that I'm interested in is Simpson's rule. Delta x over 3. This one is a little bit longer, but it usually would get you the best results. So these are the 3 that I'm interested in that I could potentially ask about. I should also remind you that for all of these, delta x is b minus a over n. Where the problem we're working on is integrating from a to b with n, I'll say vertical strips. I'm saying vertical strips because they could be thought of as rectangles. Like if it's the midpoint rule, then it's n rectangles. But we said that for the trapezoid rule and Simpson's rule, they're technically not rectangles anymore because the top of it is being sliced off in a different way. So what I want to leave you with is some general advice, is some things that you should be studying from. One is your notes and examples from class. The idea is you've been taking good notes all semester, so now's the time to use them. And you could use your notes or the schedule as sort of a checklist and kind of go through each section and say, do I know how to answer the types of problems from this section? And what about this section, right? Try to identify if you have any weaknesses and focus in on them, study them. I think, of course, there was a review packet, and that's posted on Blackboard right now as you're hearing this. And the solutions are also posted. So definitely look at that. But I'm trying to give you a little list here. Just in general, whenever I give students a review packet, I'm always worried that students are going to look at the packet and not look at anything else. So that would be a mistake. I think you want to look at your notes, look at other things. We also had that integral packet earlier in the semester. That is also on Blackboard, right? Now, I'm not going to pull up Blackboard right now, but if you go there, I started posting worksheets there on the very first day of class, right? We had kind of a little packet on the first day of class to review some integrals from Calc 1. So that's sort of the Chapter 4 stuff, maybe some substitution rule, maybe some area under a curve. So you could go back and look at those things from the first day. But we did have that day where there was a big packet that had, I think, 25 integrals. If I remember correctly, it includes integration by parts, but it doesn't include some of the later ones. It doesn't have partial fractions or anything like that. But that's 25 problems that you could look at, and then also the ones in the review packet. You could also go back and look at the quizzes we had. And you could also look at the homework we had. All right, so the MyOpenMath homework, and don't forget, look at the due date for that. But yeah, I think looking at a little bit of everything is a good idea. Well, what else can I say? It's Calc 2. You know how to study for a math test by now, but that's kind of my advice, is make sure you're studying everything. And one other thing is, remember that on the test, you're not allowed to use your notes. You're not allowed to use a calculator or a phone. And the reason I'm saying this is, as you study, it might be a good idea to try to do some of this stuff without your notes. Because it's one thing to be able to do all this with your notes, but it's another thing to show up for the test and, it's just you and the test and a pencil, and you don't have your notes. So maybe take some problems and try to study them that way, just to be ready. All right, so that's my speech. That's my advice. So get the stuff on Blackboard if you need it, and I'm here if you have any questions. Feel free to email me. All right, take care.